In the crystalline waters off the coast of Japan, a marine biologist named Sheila Patek placed a high-speed camera in front of a creature no larger than a human hand. What she was about to witness would shatter everything scientists thought they knew about the limits of biological engineering. The creature struck. The camera, recording at 40,000 frames per second, barely captured what happened next. The water itself exploded into light, a burst of plasma and cavitation bubbles that registered temperatures approaching the surface of the sun. The force of the impact measured 1,500 newtons, delivered in less than 3 milliseconds. To put that in perspective, if a human being could accelerate their arm at the same rate, they could throw a baseball into orbit. But this wasn't the most shocking part. When researchers analyzed the striking appendage itself, they discovered something that shouldn't exist in the natural world. Embedded within the creature's weapon was a structure reinforced with metal compounds, arranged in a lattice more sophisticated than anything human engineers had yet designed. This was a mantis shrimp, and its clubs contained secrets that would challenge everything we understood about evolution, materials science, and the very boundaries between organic and inorganic matter. The story begins not in the modern ocean, but hundreds of millions of years ago, in a world so alien that if you could step into it, you wouldn't recognize it as Earth. Picture the late Paleozoic era, roughly 400 million years before the first dinosaur would ever draw breath. The continents are arranged in configurations that would look utterly foreign on any map. Massive landmasses slowly grinding together to form the supercontinent Pangaea. The oceans are warm, shallow, and teeming with life forms that seem pulled from fever dreams. It's in these ancient seas that a lineage begins, a family of creatures that would eventually evolve into one of the most devastating weapons ever produced by natural selection. The early stomatopods, the ancestors of what we now call mantis shrimp, were already showing signs of something extraordinary. Their front appendages were beginning to specialize, to modify, to transform into something no other creature possessed. But what drove this transformation? What environmental pressure could possibly demand the evolution of a biological structure that could rival human metallurgy? The answer lies in the brutal economics of predation in the ancient oceans. Imagine you're a small predator in this primordial sea. Your prey consists largely of hard-shelled mollusks, crustaceans with thick armor, and other creatures that have evolved their own impressive defenses. You have two options: develop longer, sharper claws to pierce the armor, or develop a blunt weapon capable of shattering it entirely. Most predators chose the former path. But the ancestors of the mantis shrimp chose something different, something that would require millions of years of evolutionary refinement to perfect. They began developing what scientists would later call a dactyl club, a hammer-like appendage that could deliver devastating blunt force trauma. But here's where the story takes its first strange turn. Unlike a simple hammer, which might work for a few strikes before breaking, this biological weapon needed to withstand hundreds of thousands of impacts over the creature's lifetime, each one generating forces that would shatter human bone. The solution evolution arrived at was so ingenious, so perfectly engineered, that materials scientists are still struggling to replicate it in laboratories today. The structure of a mantis shrimp's dactyl club reads like something from a science fiction novel. At its core lies a region called the periodic region, composed of a substance called alpha-chitin, arranged in a helicoidal pattern that spirals through the material like a twisted staircase. This isn't random. The spiral creates a structure that can absorb impact energy and disperse it through multiple planes simultaneously, preventing catastrophic failure. Surrounding this core is the striated region, made of a different form of chitin arranged in parallel fibers, like the grain in wood, optimized to prevent cracks from propagating through the material. But the real marvel lies at the impact surface itself, a region scientists call the impact region. And it's here that evolution did something truly extraordinary. The outermost layer of the club contains high concentrations of amorphous calcium phosphate and calcium carbonate. But these minerals aren't simply deposited randomly. They're organized into a complex, three-dimensional lattice, reinforced and connected by protein bridges. Even more remarkably, this region contains significant concentrations of phosphorus and magnesium, creating what can only be described as a biological ceramic composite. But we're still not at the most shocking part. In the early 2000s, a team of researchers led by David Casailas at the University of California began examining the dactyl clubs using advanced spectroscopy and electron microscopy. What they discovered made them question their own data. Within the impact region, they found something that shouldn't exist in a living creature: metal ions, specifically high concentrations of transition metals, integrated directly into the molecular structure of the club's surface. These weren't contaminants. They weren't environmental deposits. They were being actively incorporated during the growth and maintenance of the club, woven into the fabric of the material itself by the mantis shrimp's own biology. The metals were functioning as molecular crosslinks, creating bonds between organic and inorganic components that dramatically increased the hardness and fracture resistance of the entire structure. When researchers tested the hardness of this material, they found values approaching those of certain steel alloys. A biological structure grown by a creature weighing less than a candy bar had independently evolved something equivalent to human metallurgy. The implications of this discovery sent shockwaves through multiple scientific disciplines. Materials scientists suddenly had a new model for creating ultra-hard, lightweight composites. Evolutionary biologists were forced to reconsider the boundaries of what natural selection could achieve. But the discovery also raised a profound and unsettling question. If a creature as simple as a mantis shrimp could evolve biological metal reinforcement, what other secrets might be hidden in the natural world, overlooked simply because we never thought to look? The answer to that question would lead researchers down a path that became stranger with every step. Because mantis shrimp weren't alone. As scientists began examining other creatures with a new perspective, specifically looking for metal incorporation in biological structures, they began finding it everywhere. Spider fangs, reinforced with zinc. Insect jaws, hardened with manganese. Bird beaks, strengthened with copper compounds. Nature had been practicing metallurgy for hundreds of millions of years, and we were only just beginning to notice. But to understand why evolution would go to such extraordinary lengths, we need to understand what happens when a mantis shrimp actually uses its weapon. Picture this. A peacock mantis shrimp, one of the most visually stunning species, spots a snail crawling across the reef. The snail's shell is thick, hardened calcium carbonate, evolved over millions of years to resist exactly this kind of attack. The mantis shrimp settles into position, its bulbous eyes, each capable of independent movement and possessing 16 color receptors compared to our 3, tracking the target with inhuman precision. Then it strikes. The entire attack takes place in less time than it takes a human nerve signal to travel from your finger to your brain. The dactyl club accelerates at over 10,000 gravities, reaching speeds of 23 meters per second. To achieve this, the mantis shrimp uses one of the most sophisticated biological mechanisms ever discovered. A saddle-shaped spring made of a rubber-like protein called resilin, compressed and locked into place by a specialized latch mechanism, then released all at once like a crossbow firing. When the club makes contact with the snail's shell, something extraordinary happens. The force of the impact is so extreme that it literally splits the water molecules apart, creating a phenomenon called cavitation. Tiny bubbles form in the wake of the strike, and these bubbles immediately collapse, generating shock waves and bursts of light called sonoluminescence. The temperature inside these collapsing bubbles can briefly reach several thousand degrees Kelvin. The snail's shell doesn't just crack, it explodes, sending fragments spinning through the water. The mantis shrimp has just generated a tiny, controlled explosion, using nothing but the speed and precision of its strike. But here's what's truly remarkable. After this devastating impact, after generating forces that would shatter human bones and temperatures that would vaporize organic tissue, the dactyl club remains intact. Not just intact, but ready to strike again within milliseconds. The metal-reinforced structure absorbs the impact, distributes the stress, and prevents fracture. It's a weapon that can be fired thousands of times without breaking. This raises an obvious question. How does the mantis shrimp build such a structure in the first place? The answer involves a process called biomineralization. But it's unlike any other biomineralization process known to science. Most creatures that incorporate minerals into their bodies, like the calcium in our bones or the calcium carbonate in mollusk shells, use relatively simple chemistry. Cells secrete proteins that act as templates, and minerals precipitate out of solution, crystallizing in specific patterns. But the mantis shrimp is doing something far more sophisticated. Recent research has shown that specialized cells in the dactyl club are actively transporting specific metal ions from the surrounding seawater and the mantis shrimp's diet, concentrating them and then incorporating them into the growing structure at precise locations. It's not random mineralization, it's targeted, controlled, almost engineered. The metals are being placed exactly where they're needed to maximize hardness and prevent crack propagation. But this sophistication comes at a cost. Building and maintaining a dactyl club requires enormous amounts of energy and specific nutrients. Mantis shrimp are voracious predators, partly because they need to be. They require constant intake of minerals and metals to repair and reinforce their clubs, which suffer microscopic damage with every strike. In fact, researchers have discovered that mantis shrimp periodically molt their clubs entirely, shedding the damaged outer layers and growing new ones from scratch. A process that can take several weeks and leaves them vulnerable during the growth period. During this time, they're essentially unarmed, unable to hunt effectively, forced to rely on stored energy and scavenging. It's a dangerous period, one that demonstrates just how committed evolution has made these creatures to their extraordinary weapons. The club isn't just a useful tool, it's become the defining feature of their entire biology, something they literally cannot survive without. The discovery of metal-reinforced biological structures in mantis shrimp opened a door. But what lay beyond that door would prove even more startling. As researchers began investigating the evolutionary history of metal incorporation in biology, they realized that this wasn't a recent innovation. The fossil record, when examined with new techniques and perspectives, revealed evidence of metal-reinforced structures dating back to the Cambrian explosion. That remarkable period roughly 540 million years ago, when complex life forms suddenly appeared in the ocean and unmaintained oceans with unprecedented diversity. Ancient arthropods, early ancestors of modern insects and crustaceans, were already experimenting with metal reinforcement in their mandibles and claws. But the fossil evidence was fragmentary, often overlooked or misinterpreted, because paleontologists weren't looking for it. They assumed that the presence of unusual metal concentrations in fossils was contamination, environmental deposition after death. Only when researchers began specifically testing for metal distribution patterns consistent with biological incorporation did the truth emerge. One of the most remarkable discoveries came from the analysis of Anomalocaris fossils, those bizarre apex predators of the Cambrian seas. Anomalocaris was enormous for its time, reaching lengths of over 3 feet, with grasping appendages lined with sharp spines used to capture and crush trilobites and other prey. When researchers at the Royal Ontario Museum examined well-preserved specimens using synchrotron X-ray fluorescence, they found clear evidence of zinc and manganese enrichment in the tips and edges of these appendages, in patterns consistent with biological incorporation rather than environmental contamination. Anomalocaris, 500 million years ago, was already using metal reinforcement to enhance its weapons. This meant that the biological metallurgy we see in modern mantis shrimp wasn't a recent innovation. It was an ancient strategy, refined and perfected over hundreds of millions of years of evolution. But evolution is never satisfied. The mantis shrimp's dactyl club represents the pinnacle of one particular approach to predation: overwhelming force delivered through a blunt instrument. Yet in the same family of stomatopods, in the same environments, another group of mantis shrimp took a completely different path. These are the spearers rather than smashers, and their weapons are just as remarkable, if not more so. Instead of clubs, spearers have developed elongated, blade-like appendages lined with multiple barbed spines, each spine harder than surgical steel, sharper than many manufactured cutting implements. These spines are also reinforced with metal compounds, but arranged differently, optimized for penetration and tissue damage rather than blunt force trauma. When a spearer strikes, it's not trying to shatter armor. It's trying to impale soft-bodied prey, like fish and octopuses. The attack is just as fast, just as explosive. But instead of a hammer blow, it's like being hit by multiple hypodermic needles moving at superhuman speed. The diversity of approaches within the stomatopod family reveals something profound about evolution. Given the same basic body plan and the same environmental pressures, natural selection explored multiple solutions, each one optimized for a slightly different niche. Smashers hunt hard-shelled prey and live in rocky reefs where their hammering strikes can't easily miss. Spearers hunt soft, fast-moving prey and often live in burrows, striking from ambush. Both developed metal reinforcement, but applied it in fundamentally different ways. This demonstrates that metal incorporation isn't just a one-time evolutionary accident. It's a versatile strategy that can be adapted and optimized for multiple purposes. And if mantis shrimp could do it in 2 different ways, what else might be possible? What other biological weapons might be hiding in the world's oceans, reinforced with metals we haven't yet discovered? The question becomes even more intriguing when we consider the biochemical challenges involved. Metals, in high concentrations, are toxic to most living cells. Iron, zinc, copper, manganese, all essential nutrients in small amounts, but deadly in excess. They generate reactive oxygen species, disrupt cellular membranes, interfere with enzyme function. For a creature to intentionally concentrate metals in its tissues requires sophisticated detoxification and sequestration mechanisms. The mantis shrimp must have evolved entire biochemical pathways dedicated to safely transporting, storing, and incorporating metals without poisoning itself in the process. Recent genomic studies have begun to identify some of the genes involved, including specialized metallothioneins, proteins that bind metal ions and prevent them from causing damage, and unique transport proteins that shuttle metals specifically to the growing dactyl club. But we're still only scratching the surface of understanding how this system works at a molecular level. What makes this even more remarkable is that mantis shrimp aren't just incorporating any metals they find. They're selective. Analysis of dactyl clubs from different species, living in different environments with different available metal concentrations, shows consistent patterns. The same metals appear in roughly the same proportions, regardless of what's most abundant in the environment. This means mantis shrimp are actively seeking out and concentrating specific metals, presumably because those particular metals offer the best mechanical properties for their purposes. They're making choices, in an evolutionary sense, about materials engineering. They've solved problems that human metallurgists still struggle with. How to create a lightweight, ultra-hard, corrosion-resistant material that can withstand extreme repetitive stress without fatiguing. And they did it without foundries, without computer modeling, without any of the tools we consider essential for materials science. They did it through millions of years of trial and error, with natural selection as the quality control. But the story takes an even darker turn when we consider the implications for ancient marine ecosystems. If mantis shrimp today, relatively small creatures, possess weapons this devastating, what about their ancestors? What about the stomatopods that lived during the Jurassic or the Cretaceous, when marine life reached sizes that dwarf anything alive today? The fossil record is frustratingly incomplete when it comes to soft tissues and detailed biochemistry. We have shells, bones, occasional impressions of skin or muscle. But the delicate structures of a dactyl club, the precise arrangement of metal-reinforced tissues, these rarely fossilize in ways we can detect with conventional methods. However, in a few remarkable specimens, preserved in limestone deposits formed in oxygen-poor environments, where decay happened slowly and mineral replacement was rapid, researchers have found tantalizing hints. Fossil stomatopods from the late Cretaceous, some significantly larger than modern species, show evidence of appendage structures that, when analyzed for trace metal distribution, reveal patterns consistent with metal reinforcement. Imagine for a moment a mantis shrimp the size of a large dog, living in the shallow seas that covered what is now Kansas 75 million years ago. Its dactyl clubs would have been enormous, capable of generating forces measured in tens of thousands of newtons. What could such a creature hunt? What would need to die to satisfy its predatory needs? The answer likely includes ammonites, those coiled shell cephalopods that dominated Cretaceous oceans, some growing to sizes rivaling car tires. Their shells, though thick and reinforced, would have been vulnerable to sustained attacks from a large mantis shrimp. We might never find direct evidence of this predation in the fossil record. Predator-prey relationships are notoriously difficult to document in deep time. But the circumstantial evidence is compelling. Large stomatopods and large ammonites coexisted in the same environments, and basic predator-prey dynamics suggest they must have interacted. The extinction of the non-avian dinosaurs 66 million years ago, caused by an asteroid impact in what is now Mexico's Yucatan Peninsula, fundamentally restructured marine ecosystems. Many large marine predators disappeared, including mosasaurs, plesiosaurs, and numerous species of large sharks and fish. Ammonites went extinct entirely, but stomatopods survived. They made it through the mass extinction event, and in the aftermath, in the Paleogene epoch that followed, they diversified rapidly, adapting to new ecological niches left vacant by the extinction. This survival raises fascinating questions. What allowed stomatopods to endure when so many other marine predators perished? Was it their relatively small size, which required less food and allowed them to subsist in disrupted ecosystems? Was it their burrow-dwelling lifestyle, which offered protection from environmental chaos? Or was it something about their unique biology, their metal-reinforced weapons, their extraordinary vision, their metabolic flexibility, that gave them an edge? We may never know for certain, but the fact that they survived and thrived suggests that the evolutionary investment in biological metallurgy paid dividends beyond just effective predation. In the modern ocean, mantis shrimp occupy a unique ecological position. They're not apex predators in the traditional sense. They're too small, and plenty of larger predators eat them. But within their size class and habitat, they're nearly unstoppable. Fish avoid them. Octopuses avoid them. Even sharks have been documented changing course to avoid mantis shrimp burrows. Their reputation is well earned. There are documented cases of mantis shrimp breaking aquarium glass, shattering laboratory equipment, injuring researchers. One particular incident, widely reported in the marine biology community, involved a peacock mantis shrimp that systematically destroyed over $2,000 worth of equipment in a research lab over the course of several months, smashing glass containers, cracking plastic housings, and generally causing chaos before researchers finally managed to relocate it. The creature was nicknamed Tyson, after the boxer, and became something of a legend. But beyond the anecdotes and the humor, there's something genuinely unsettling about a creature this small, possessing weapons this powerful. It suggests that we've fundamentally underestimated the potential of biological systems. We tend to think of technology, of engineering, of materials science as uniquely human achievements. We build skyscrapers, forge steel, create composites and alloys and ceramics. But nature was doing all of this first, and in many cases, doing it better. The mantis shrimp's dactyl club outperforms many human-engineered materials in specific metrics. It's lighter, more durable, self-repairing, and grown at ambient temperature and pressure using materials extracted from seawater. No furnaces, no factories, no industrial processes, just biology, running on the energy from sunlight captured by algae and passed through the food chain. When materials scientists study mantis shrimp clubs, they're not just satisfying curiosity, they're hoping to learn lessons that could revolutionize human technology. This has already begun to happen. Research teams at multiple universities and corporations are actively working on mantis shrimp-inspired materials. The goal is to replicate the helicoidal structure, the layered composite architecture, the metal reinforcement strategies, all using manufacturing techniques humans can actually implement. Some progress has been made. Using three-dimensional printing and advanced composite materials, researchers have created synthetic materials that mimic some properties of the dactyl club. These materials show promising applications in aerospace engineering, where lightweight, impact-resistant structures are critical. They're being explored for body armor, where the ability to absorb and disperse kinetic energy could save lives. They're being considered for infrastructure, for buildings and bridges that need to withstand earthquakes and storms. The mantis shrimp, a creature most people have never heard of, might end up contributing to fundamental advances in human civilization. But we're still decades away from fully replicating what evolution achieved. The precision of metal placement, the molecular level control over structure, the self-assembly processes that occur during growth. These remain beyond our current capabilities. We can approximate. We can create materials inspired by mantis shrimp biology, but we can't yet match it. This humbling realization has led to a shift in perspective among some researchers. Instead of viewing nature as something to dominate or exploit, they're beginning to see it as a library of solutions, a vast repository of engineering knowledge accumulated over billions of years of trial and error. Every organism represents a different experiment, a different approach to the fundamental challenges of survival. And some of these experiments, like the mantis shrimp's biological metallurgy, represent insights we haven't discovered on our own. The philosophical implications extend even further. If a creature can evolve metal-reinforced weapons, what else might evolution produce given enough time and the right selection pressures? Could biological structures approach the hardness of diamond? Could creatures develop biological electronics, living circuits that process information using electrical signals in ways more sophisticated than neurons? Could there be organisms somewhere, perhaps in extreme environments we haven't fully explored, that have evolved capabilities we consider impossible for biology? The deep ocean remains largely unexplored. Vast regions of total darkness, crushing pressure, and bizarre chemistry where life exists in forms we're only beginning to catalog. Hydrothermal vents, cold seeps, abyssal plains. These environments host creatures adapted to conditions that would kill surface-dwelling organisms instantly. What might they have evolved? What secrets might they hold? Some researchers are taking this question seriously. There are ongoing efforts to systematically survey deep-sea organisms for unusual material properties, specifically looking for metal incorporation, unusual crystal structures, exotic biochemistry. It's slow work. Deep-sea exploration is expensive, time-consuming, and technically challenging. But the potential payoff is enormous. If we could find even one creature that has evolved a capability fundamentally different from anything currently known, it could open entirely new fields of research. And given the track record of unexpected discoveries, the mantis shrimp's dactyl club being just one example among many, there's every reason to believe such discoveries are out there, waiting. The mantis shrimp itself continues to reveal new surprises. Recent research has shown that their vision, already known to be extraordinarily sophisticated with 16 color receptors and the ability to see polarized and ultraviolet light, is even stranger than previously thought. They don't process color information the way we do. Instead of comparing signals from different receptor types to derive color perception, as human vision does, mantis shrimp appear to use a scanning system, rapidly moving their eyes and sampling different wavelengths sequentially. This is a completely different approach to vision, one that might allow for faster processing at the cost of some accuracy. Why would they evolve such a system? Possibly because speed is everything when you're a predator that relies on ambush attacks measured in milliseconds. They need to identify prey, assess distance, and strike before the target can react. Conventional color processing might be too slow. Even more remarkably, some species of mantis shrimp appear to use their color vision and their ability to see polarized light for communication. They have polarized patterns on their bodies, invisible to most predators, but clearly visible to other mantis shrimp. They may be signaling territory boundaries, mating availability, or threat displays using a visual channel that only they can access. It's a secret language, encoded in the structure of light itself. And we only discovered it recently because we finally built cameras sensitive enough to detect the polarization patterns. This raises an uncomfortable question. How many other forms of communication, of sensory perception, of interaction with the world might exist around us? Invisible simply because we lack the biological equipment to detect them. The mantis shrimp sees a richer, more complex world than we do, and uses weapons we can barely replicate. What does that say about our place in nature? The story of the mantis shrimp is, in many ways, a story about humility. It's a reminder that intelligence and technology, as impressive as they are, represent only one solution to the challenges of survival. There are other solutions, evolved solutions, that can be just as effective or more so. A mantis shrimp doesn't understand materials science. It can't explain why its dactyl club works. It simply inherited a weapon refined over millions of years of evolution. And it uses that weapon with extraordinary effectiveness. Yet that weapon embodies principles of engineering that human scientists are still working to fully understand. This suggests that intelligence might not be the most important factor in innovation. Time might matter more. Iteration might matter more. The relentless, unforgiving process of natural selection, testing endless variations over geological timescales, might discover solutions that no individual genius could conceive. This has implications for how we approach technology and innovation in our own civilization. We tend to focus on breakthroughs, on sudden leaps of insight, on individual brilliance. But perhaps we should be paying more attention to iteration, to gradual refinement, to the slow accumulation of small improvements over long periods. Perhaps we should be more willing to learn from nature, not by blindly copying what we see, but by understanding the underlying principles and adapting them to our needs. The field of biomimicry, which seeks to do exactly this, is still relatively young, still establishing its methodologies and proving its value. But examples like the mantis shrimp suggest it has enormous potential. If we can learn to think like evolution thinks, to test and refine and optimize the way natural selection does, we might discover solutions to problems we currently consider unsolvable. In a research facility in Singapore, scientists are raising mantis shrimp in controlled laboratory conditions, studying their development from larvae to adults, documenting the growth of their dactyl clubs in unprecedented detail. High-resolution imaging captures the formation of each layer, the deposition of each mineral, the incorporation of each metal ion. The goal is to understand the complete developmental process, from genetic activation to final structure. If they succeed, if they can map out every step of how a mantis shrimp builds its weapon, they might be able to replicate it. Not with biology, but with nanotechnology, with molecular assembly, with precision manufacturing at scales we're only beginning to master. It would represent a convergence of natural and artificial engineering, a fusion of solutions discovered by evolution and solutions created by human intelligence. But even if we succeed in replicating the mantis shrimp's dactyl club, even if we create materials that match or exceed its properties, we won't have truly understood it. Understanding isn't just about knowing how something works. It's about knowing why it works, about grasping the deeper principles that make it possible. The mantis shrimp's weapon is the result of countless evolutionary trade-offs, compromises, accidents, and innovations stretching back hundreds of millions of years. It exists within a context, an ecological web of predators and prey, threats and opportunities, energy flows and material cycles. To truly understand it, we'd need to understand that entire context. And we're far from achieving that level of comprehension. We're still cataloging species. We're still mapping ocean currents. We're still discovering basic facts about marine ecosystems. The gap between our knowledge and true understanding remains vast. Perhaps that's as it should be. Perhaps there's value in mystery, in knowing that there are things we don't understand, can't predict, haven't yet discovered. The mantis shrimp exists in oceans we've barely explored, using weapons we can barely replicate, seeing colors we can't perceive, living a life we can only dimly imagine. It's a reminder that the world is larger and stranger and more complex than we often remember. We spend our days in constructed environments, surrounded by human artifacts, interacting mostly with other humans. And it's easy to forget that we share this planet with millions of other species, each one solving the puzzle of survival in its own unique way. Some of those solutions are gentle, subtle, almost invisible. Others, like the mantis shrimp's metal-reinforced hammer, are anything but. Somewhere in the coral reefs of the Indo-Pacific, right now, a mantis shrimp is settling into position. Its eyes, mechanical jewels capable of seeing dimensions of light we cannot imagine. have locked onto prey. The specialized muscles in its second thoracic appendages are contracting, compressing the saddle-shaped spring, storing energy like a crossbow being drawn. The latch mechanism holds everything in place, tension building, potential energy accumulating. In the dactyl club, hundreds of millions of years of evolutionary refinement wait to be unleashed. The helicoidal structure, the layered composites, the metal-reinforced impact surface, all working in perfect concert. The creature doesn't think about any of this. It doesn't marvel at the engineering. It simply acts, releasing the latch, allowing the spring to uncoil, accelerating the club to speeds that blur the boundary between liquid and vapor. The strike lands. The water explodes into light and heat. The prey shatters. And the mantis shrimp, ancient and alien and utterly remarkable, feeds. The sun moves through the sky. Tides rise and fall. Ocean currents flow in patterns older than continents. And in the spaces between coral heads, in the crevices of rocks, in burrows dug into sand and mud, mantis shrimp wait. They've been waiting for 500 million years, outlasting countless other species, surviving mass extinctions, adapting to changing oceans and shifting climates. They're still here, still hunting, still wielding weapons that challenge our understanding of what biology can achieve. We've begun to notice them, to study them, to learn from them. But we're newcomers to their world, recent arrivals on an evolutionary timescale. They've been perfecting their craft since before the first fish crawled onto land, before the first forest grew, before the first flower bloomed. And they'll likely be here long after we're gone, assuming we don't destroy the oceans first. That's perhaps the final lesson the mantis shrimp has to teach us. Sustainability, endurance. The ability to persist not through domination or rapid expansion, but through perfect adaptation to a specific niche, through the patient refinement of capabilities over timescales we struggle to comprehend. Human civilization is young, perhaps 10,000 years old if we're generous. We've achieved remarkable things in that time. But we've also created existential threats that our ancestors never had to face. Climate change, pollution, habitat destruction, resource depletion. We're testing the limits of our environment's resilience, and we don't know where those limits are. The mantis, shrimp, and countless other species like it demonstrate an alternative approach. Exist within the limits, use what's available, waste nothing, persist. They're not trying to transcend their environment. They're not trying to grow exponentially. They're simply being what evolution made them, as perfectly as possible. In the end, the story of the mantis shrimp and its impossible weapon is really a story about perspective. From our human viewpoint, with our tools and technologies, with our ability to extract and refine and forge metals into shapes we find useful, the idea that a small marine creature could develop biological structures approaching the hardness of steel seems absurd. But from evolution's perspective, from the viewpoint of a process that has had billions of years to experiment and billions of organisms to test variations upon, there's nothing absurd about it at all. It's simply one solution among countless others, one strategy for survival in a complex and dangerous world. And the fact that we're only now beginning to appreciate it, to study it, to learn from it, says less about the mantis shrimp than it does about us. We're learning to see with new eyes, to ask questions we didn't know enough to ask before, to recognize engineering genius wherever it appears, even in creatures we once dismissed as simple animals. The ocean keeps its secrets well. For every mystery we solve, we uncover 10 more. The mantis shrimp's metal-reinforced weapons are just one example, one thread in an infinitely complex tapestry of adaptations and innovations that fill every marine ecosystem. What else is out there, waiting to be discovered? What other impossible structures exist in creatures we've never studied closely? What other forms of biological engineering have evolved in the deep sea, in polar waters, in places too remote or extreme for easy investigation? The answers to these questions could reshape our understanding of what's possible, could inspire technologies we can't currently imagine, could reveal principles of organization and efficiency that apply far beyond biology. Or they might simply deepen the sense of wonder, the recognition that we inhabit a world stranger and more creative than our imaginations can compass. Night falls on the reef. Darkness is never complete here. Bioluminescence provides a dim, ghostly illumination as countless organisms generate light through chemical reactions perfected over millions of years. The mantis shrimp emerges from its burrow, eyes scanning the darkness, seeing wavelengths and polarizations invisible to most other creatures. It moves through the reef with purpose, a hunter perfectly equipped for its role, carrying weapons forged in the slow fires of evolutionary time. Somewhere in the darkness, prey waits, unaware. The ancient dance continues. Predator and prey, strike and response, the eternal struggle that drives innovation and refinement, and the slow accumulation of impossible adaptations. And we, watching from the shore or from behind cameras and aquarium glass, are only beginning to understand what we're seeing. The story isn't finished. It never is. Evolution continues, relentless and patient, testing new variations, exploring new possibilities. The mantis shrimp lineage will continue to evolve, adapting to changing oceans, responding to new pressures, perhaps developing capabilities we can't yet imagine. Human understanding will continue to deepen as technology improves and more researchers turn their attention to these remarkable creatures. The intersection of biology and materials science will produce new insights, new applications, new technologies. But beneath all the research and analysis and innovation, the fundamental truth remains. We share this planet with creatures whose capabilities exceed our own in specific, remarkable ways, and there's profound wisdom in recognizing that fact. We are not the measure of all things. We are one species among millions, one solution among countless others, one brief experiment in the long history of life on Earth. The mantis shrimp, ancient predator with impossible weapons, bearer of secrets we're only beginning to decode, exists as a reminder of that truth. And if we're wise, we'll remember it.